Alright, so this is lecture 2. Here I have only, I think, 14 slides, 13 or 12. So maybe, yeah, let's see. Let's see. So the outline, like I said, we'll be discussing about the properties of aquifers, after which we will discuss about the steady and unsteady flows, particularly referring to the Darcy's law, and then the flow analysis in confined and unconfined aquifers. All this, if you look at the description, they are all under reviews, isn't it? They are all under what? Reviews. So we haven't yet started the groundwater modeling proper. We are just reviewing some basic concepts, okay, which you have done before. So even the properties of aquifers is nothing, we'll say nothing new, probably, okay? But like I said, there will be no assumption. Just because you did it before, we won't ignore them. We'll still drill and ensure that the correct information is passed, okay? So, properties of aquifers. The properties of aquifers is important in the following areas. 1, planning and management of groundwater resources. We need to know and understand the properties of these aquifers when planning and managing any groundwater resources. As we move deeper, you will understand why this is so important, or why this is so. Because it will help us in quantitative evaluation. To know the quantity in the groundwater. Is the quantity that much? Is it at is the water present at economic rates that is worth exploring or not? And it gives us also about ideas about reliability, reliable interpretations, and descriptive understanding of the aquifer, and then comprehensive idea about temporal variability of groundwater system. Temporal referring to time, isn't it? Over time it changes, because that's one of the things we'll be dealing with when looking at the groundwater modeling aspect. Over time, how is the pressure head affected? How is the piezometric head, the hydraulic grade line, how does it change over time under so conditions, under given conditions? Okay? And the important aquifer properties that we have are generally classified into 3. Generally, we have storage properties, we have transmission properties, and we have others. We'll take each one of these and explain. Under the storage properties, we have the porosity, total porosity. If you remember, we have started talking about the porosity, primary and secondary, and effective porosity. And then we have the specific yield, and specific retention and storativity, and specific storage. All this you have done them in REN 503, and then even here probably 701 or whatever you call it at the MS level. Okay, but still we will go down and just brush over. Then we have the transmission properties of an aquifer. Under this we have the hydraulic conductivity, or the permeability, isn't it? Permeability and transmissivity. And then we have others that also affect the aquifer storage, which is the isotropy and heterogeneity. Okay? So we'll pick each of these and then move on. But like I said, probably if I ask you what is the definition of porosity, you all know what that is, isn't it? But at this level, we have gone beyond cramming, memorizing, cramming formulas and definitions. No. We are at a level where we need to internalize, we need to really understand what all this definition truly means in practice. Okay? All right. Like I said, we'll pick each one of them as we move on and explain. Porosity, which is one of the storage properties and one of the most important properties of an aquifer. is the porosity. And here we'll talk about 3 types of porosities, okay? Primary porosity, secondary porosity, total porosity, which is classified into primary and secondary, and then effective porosity. The water holding potential of a medium is given by its porosity. Water holding potential. Underline that word. Water holding potential. Okay? The ability of an aquifer to hold water is given by its porosity. Now, we have primary porosity, which is the original interstices created when the soil or rock was formed. It's called primary porosity, while the secondary porosity is the solution enlarged openings, joints or faults in carbonate and other soluble rocks. Because over time, when you have soluble rocks, water is going through, or acid, because usually in the underground, you may have some acids. You have acid mine drainage. Okay? You may have some acids because as the groundwater is coming in contact with some rocks, some geologic formation, it dissolves. Okay? It dissolves some of these acids that are inherent in this formation, and then move along with it. And then at the same time, we have water, because the main source of recharge, the main source of water of the ground, constituting the groundwater, is from rainfall, precipitation, isn't it? When you have water coming in contact with carbon dioxide, what do you have? You have carbonic acid, isn't it? Which is a weak acid. Am I right?
Yes.
So, water in the atmosphere is interacting with carbon dioxide. And now with global warming, we are constantly generating CO2 at alarming rate, isn't it? So even in the atmosphere, it interacts. Or when falling from the atmosphere, it interacts with CO2 to form carbonic acid. And then it goes deeper down from the unsaturated zone to the saturated zone. Okay? And this also could happen as a result of reaction. This carbonic acid can happen when water interacts with some of the salts in the unsaturated zone. Carbonic acid can also be formed. So sometimes you have the groundwater to be a bit acidic. And what is the implication of that? Is that it can erode when you have carbonate rocks. It can now dissolve them, isn't it? It can now dissolve them and create some spaces here and there, thereby increasing the porosity. So the secondary porosity is the one that is obtained, or which is constantly being reshaped depending on the soil matrix, depending on the geologic formation, isn't it? Which is constantly being reshaped as a result of some processes taking place. Okay? And then porosity depends on the degree of compaction of grains. The degree of compaction of grains. And the grain size. I'm sure it is there. Particle size distribution. Degree of compaction of grains, shape of grains, and particle size distribution. This is something we know, isn't it? The more compacted it is, the more the void spaces will be filled up, isn't it? And the shape of grains, the smaller they are, probably, the more they will fill all the sizes, all the void spaces, and then the lower the porosity. And then the particle distribution. If it is well graded, it means you have bigger particles, average and small. The smaller particles will fill the void spaces, isn't it? And then the porosity will be affected. Is that clear? And the same thing when you have coarse particles. In that case, if you don't have smaller particles filling in the void spaces, it will have higher porosity. Okay? And a porous media containing mixture of grains will have low porosity, because the smaller grains will fill the void spaces, isn't it? So it will have lower porosity. Still on porosity, it may range from 0 to more than 60%. By percent here, it means the void space within the soil matrix can be greater than 50%. Okay? From 0 to more than 60%, depending on the soil type, depending on the grain size, depending on the gradation, the particle size distribution. Okay? And it averages about from 25 to 35% for most aquifer systems. That's the average value for most aquifer systems. Porosity increases as depth decreases. Why? Why does it decrease? It increases as depth decreases. So we're moving up, isn't it? It increases. Let's say this is the ground surface. If this is the ground surface, as the depth from the ground surface decreases, N increases, the porosity increases. Meaning, when going down, as depth increases, N decreases, right? Why is it so? Because you saw what I wrote. Oh, he saw the answer. So, what do you mean by the level of compaction? What? So how does you will still have to explain further. You still did not hit what?
Your body as you go down pressure is much as a way down above this. That's what the compact is only completely.
At the top level, the soil has been disturbed. So as a result, it's mostly.
The soil has been disturbed?
Yes.
How so?
Various activities.
Disturbed? Yes. We call it undisturbed soil, isn't it? When taking any geologic, any geotechnical investigation.
We can call it undisturbed soil, but as it goes further, there's no any level of distortion. I mean, it's undisturbed, but we can
Okay. Go ahead.
It's because as you go down, the volume of the soil matrix, the porous media is larger than the volume of the void. So that's why.
What?
The total volume of the soil is larger as you are going down. So compared to the volume of the void, so the volume will increase. The soil volume will increase as you're going down, while the increment is very little. So
can you talk about the void? The void volume.
Void volume, yes, sir.
Instead of the soil volume.
I should talk about.
No, rephrase your answer by referring to void volume rather than the soil volume.
What means that the void volume decreases as you go down. That's all.
Why? Why does it decrease?
Because of the degree of compaction.
Okay, that's exactly what I want to hear. Okay? Because as you go deeper down, the pressure, you mentioned about the overburden pressure, is higher, isn't it? Because it's a function of the height. So, the higher the overburden pressure, the more compacted the soil becomes. And therefore, the less the void space. The void space will be filled more easily because of the compaction. Some of the soil matrix will be crushed, and then the void space will reduce. Is that clear? All right. Don't worry, we will have many more whys. Okay? We'll have many more whys. This is on account of the weight on top of the deeper materials, compaction and pressure solution. Porosity also tends to increase with grain size. Why? It tends to increase with grain size. As the grain size increases, the porosity increases. Why is that?
You said when we have defined grain,
and the one that filled with more grains, meaning fine grains, there will be low porosity. So when we have the larger one, there will be more space in between, so the porosity will be high.
Okay. Because here we said large, it increases with grain size. Because as the grain size increases, also the species increases. And this is, we are referring to soil matrix that is not well graded. For well graded soil, then that is different. Okay? And then we have the intergranular porosity, which is intergranular porosity between grains, mostly part of the effective porosity, but also dead end pores. Is the porosity between grains, mostly part of the effective porosity, but also dead ends. The intergranular porosity also includes what is called dead end. By dead end, you may have this, and then probably you have one big blocking everything. So here you see, and then this is a dead end, right? The interstices here are connected. Can you see that? But here is a dead end. Here is a dead end, isn't it? So that's the intergranular, between grains. And then you have intragranular porosity. Within grains, within the same grains, it can have some pores. Okay? Because the soil has pores. You know what's activated carbon, right? Activated carbon. Oh, you will tell me you are not in environmental engineering, so you don't need to know. But that is not acceptable. Because even in your MSc or PhD, it will be written water resources and environmental engineering. So you don't know what is activated carbon? You know? Okay. So why do we use activated carbon? And how does that happen? Large surface area. And what constitutes the surface area? The pore spaces, it is highly porous. It has pores inside intergranular porosity. Okay? So what about soil now? That's activated carbon on one side. What about soil? Does it has pores inside, like activated carbon?
Are you talking about granular materials?
Yes. The soil has pores within the soil grains, like activated carbon?
It depends on the uniformity coefficient. This is the decomposition of the soil.
Uniformity coefficient. What is uniformity coefficient?
That is the size of the particles in the middle of the
Does uniformity coefficient has anything? Does it have anything to do with the pores? The uniformity coefficient? No, not size. We're not talking about size. We're talking about pores, inner pores, internal pores within a soil grain. And that can only be expressed in terms of the surface area. The surface area of the soil. So, does soil have internal pores like activated carbon? Huh?
Yes.
It has? What? What?
Yes. Depending on what constitutes the granular materials.
Depending on the soil type or what?
Yes. That's what particles that make up the soil.
So which one will be more porous, will have more porous, larger surface area than the other? Which one?
The one that has granular materials are porous.
Okay, now name the soil type.
Yes.
Which one?
Yes. Sand.
Coarse sand? No, you are not talking. You are not being specific. A coarse sand can be made up of a lot of different materials, of different geologic materials. Okay, we have different soils, right? although we are not, you did engineering soil science, so like even the capillary pressure, I wanted to mention that. Do you have class now? After at 10?
After, yes.
Huh?
After 10.
After 10? So you have another class. Okay, just give me a few minutes. Okay? Just give me a few minutes. I thought you don't have anything because I came 20 minutes late, so I wanted to compensate for that 20 minutes.
You can compensate, sir.
But then,
The environmental engineers.
yeah, they can attend if they so wish. Now, we were talking about soil, right? Okay. We have different types of soils. You might hear about kaolinite, montmorillonite, elite. All this you must have done it in geology for engineers. Is it soil mechanics? Soil mechanics? And also soil science? Okay. Whichever course it is, all I know is that you must have done it, isn't it?
Yes.
It can be engineering soil science. Yes, it can be soil mechanics or even geology. You have montmorillonite, kaolinite, elite, and many of them. Because soil can be classified based on so many things. This is classified based on what is called, you have 2-to-1 clay mineral, you have 1-to-1 clay mineral. That is about clay itself. Okay? So, the one that has the high surface area is called montmorillonite. It has very good surface area, sometimes close to that of activated carbon. Montmorillonite. It is also called expansive soil, expansive soil, because you put small amount of water, it expands. It sucks. Okay? So, yes, some clay minerals, depending on the type, it may be highly porous. It may have high surface area, depending on which soil you are talking about. Montmorillonite in particular has high surface area. Okay? Now, intragranular porosity. Within grains, usually not considered part of the effective porosity. It is not considered part of the effective porosity because usually it may not constitute groundwater flow. They are internal pores. Now, what is effective porosity? Oh, okay. We are just going there. How do you determine lab determination of porosity? How do you determine it? N equals 1 minus bulk density over the solid density. That takes us to soil mechanics, isn't it? Soil mechanics. I'm sure you have done this in the lab, isn't it?
We went to the lab, sir.
You went to the lab,
We went to the lab.
but you don't know what you did.
We were so many that we couldn't even see what they were in. And the last person sent us out.
All right. Now is the time. How do you determine it in the lab? There is some simple way probably to do it, but you can do this by determining the bulk density over the solid density. Because the bulk density is different from the solid density. Okay? But then there is another simple way of doing that, because the total volume over the volume of the void. If you can have your soil matrix in a container, measure its volume, and then put amount of water, a measurable amount of water, until it is fully saturated. Then if you can know the amount of water which you poured, it must have occupied all the void spaces. And then you can now take the ratio. The volume of water over the total volume before pouring the water. Do you understand? So this is like an approximate way of determining the porosity under lab condition. Okay? In addition to this one. Of course, you have other methods. Okay? Now,
So, below S, is it the dry density? Dry soil density?
the solid density.
Dried one.
Yes, definitely. And then this is the bulk density. And now if I ask you about what is the difference between the solid and the bulk, go and review your soil mechanics. Okay, I'm sure you are very much, up to date about this. Okay? You see, porosity is one of the input into our model. So we need to understand exactly what it is. How do you determine it? Because for any modeling process, be it under lab condition or under field condition, you need to determine the porosity. If you cannot determine it, what are the different ways by which you can get an approximate value for it? Because nothing is perfect. Even our modeling is not perfect. We are just trying to approximate, to be close to reality. So you may find yourself having to determine the porosity under field condition, or, oh, he is here. So we have to, no, just 3 minutes and I will pack my thing. 3 minutes.
Okay, I'm actually busy with this verification.
Okay, so you will not be attending because I have just 9 minutes to round up.
Okay, just round up.
Okay.
I may finish in 30 minutes.
Okay, so just 9 minutes. Yeah?
Yes.
So there's clash or what?
Then they will just move to the conference room.
All right, so like I said, each of these properties now will explain from what you know and then the lab determination, because they will be serving as input into our model. So as such, you must understand them. You must understand how to determine it under lab condition, because you are all postgraduate students. Most of you probably have started your work, your research, and what have you. And you may find yourself in a situation whereby you will need to determine these properties, or you may need to use them. So you will have to know how to determine them under lab or field condition. Yes.
Sorry, you said something there. You made mention of us measuring is it the volume you say or the weight of the soil inside a container then we now, or what?
The volume of the soil, because what is porosity? Volume of the total volume over the volume of the voids. So if the void is filled with water, completely filled, then you use the volume of water, which is used in filling the void spaces, isn't it? So it's an indirect way of determining the porosity, more or less like an approximate method. Okay? Yes. Although, as we are going to mention, for our groundwater case or cases, we don't use the total porosity. We use the effective porosity, which will be in the next slide. Yes, what do you want to say?
You have talked about the effective porosity, and you don't talk about the primary porosity.
No, I talked about the primary. The primary porosity is when the soil is formed. Original interstice is created when the soil was formed. And the secondary porosity, that is like modified over time due to openings, solution enlarged openings. Because you have more or less like an acidic water that is in interaction with the soil matrix, which is constantly reshaping the voids. So that's the solution enlarged openings or joints, faults, and what have you. And that is the secondary porosity. Okay, this I explained. Probably your mind has gone far beyond the shores of Nigeria. Okay? Now, coming back or going down to effective porosity. In groundwater, we are referring to the saturated zone. In the saturated zone, you have groundwater flow, isn't it? For groundwater to flow, you must have a continuous channel, isn't it? Because as we are going to the Darcy slope, it's assumed that you have like more or less like an open channel flow. Okay? You have a continuous channel through which the groundwater will be flowing, through the interstices. It will be tortuous, definitely. You have grain here, there, here, okay? And then it will be following through the interstices, isn't it? The path is what? Tortuous. Maybe later when discussing the contaminant transport, we may talk about tortuosity. Okay, but the path is tortuous. But of course, it has to be what? Connected. The void spaces have to be connected. If not, if this is like not connected, you see, this is like a dead end, then, okay, probably it will now move here, isn't it? If there is another path, isn't it? So what are we talking about here? Connected interstices. That is the one, or they are the ones that will now constitute groundwater flow. The connected interstices, not just the overall void space. The overall void space, some of them could be connected, and some will lead to dead end, and that will not constitute groundwater flow. Do you understand? And that's exactly what the effective porosity is talking about. The connected interstices, the connected void spaces. Is the ratio of volume of the interconnected interstices to the total volume of the aquifer, rather than the total porosity, which is just the total volume of the voids only, irrespective of whether they are interconnected or not. Are you following? Not all pores participate meaningfully in the flow of water, just as I finished explaining. Effective porosity is more related to the flow of groundwater in a medium than total porosity. These can differ significantly. So you don't just say, I have the total porosity is just approximately equal to this. No. It means, but now from this, which one will be higher? Is it the total porosity or the effective porosity? How will you relate them in terms of which one will be higher? What? Total porosity, because it includes additional pores that are not interconnected, isn't it? All right. When all pores are connected, then total porosity equals effective porosity. It is assumed to be uniform spatially and temporally, thus neglecting any elastic storage effect that may arise under transient flow conditions. It is assumed to be uniform spatially and temporally. But of course, as we move into the modeling proper, sometimes we may make it variable, because in the real sense, it is assumed to be uniform so as to make it just like one value. If not, it will have to be expressed in all the dimensions, in X, Y, Z, and time. Because as we are going to, as we have based on our explanation, the porosity also varies with time, isn't it? But these may be small changes that we can ignore and assume that it is uniform spatially and temporally. Okay? But these are some of the guiding assumptions that every model must have. You must present your assumptions. What and what are you not considering? What and what are you pegging to be constant or variable? Okay? Lab determination. How do you determine it? This is the ASTM standard, practice for description and identification of soils. This is the standard that is used to determine the effective porosity. But in the lab, how do you determine the effective porosity? To determine the effective porosity, you have saturated your water, you have your soil in a particular column, okay? And then you know the volume of soil, you saturate it from the top, and then when it is fully saturated, you now have like a stopper here which you open to drain the water. You collect the amount of water. Of course, you try to cover it so that there will be no evaporation. Okay? You collect the amount of water that is able to be drained. And that, the volume of water over the total volume of soil will constitute the effective porosity. Because some of the water would have been detained or retained, which means it is not free to flow down. So that will constitute effective porosity. In my next class, that will be next week on Thursday, we'll talk about specific yield and specific retention as some of the most important properties of an aquifer. And from this, you see, we dealt with porosity because, like I told you, it's one of the most important property when it comes to input into our model. Okay? And as such, we need to understand it very well. So any question before we call it a day? And then I will take my attendance. Is anybody here that is not on my attendance list? Any new person? Okay, let me open the attendance list and then probably What? Yeah, you have question, right?
Yes, sir.
Mm-hmm.
You said if we want to measure the effective porosity, it's just similar to the same way we do for the normal porosity. But my question is this.
No, I didn't say it's normal. It's the same.
We measure the soil before it's saturated.
What?
We measure when we add water to it, then before we add water to it.
Yes. No, you measure the amount of water used to saturate it, not the total. Yeah, you measure the amount of water used to saturate the soil. Yeah.
The soil is saturated before saturation, the volume.
Yeah.
Then this one is water you drain from the soil.
Exactly.
And
The drainable water.
That you pour are retained.
My question is not even about the water.
Okay, then go straight to your question.
Is, you made mention of interconnected
Interstices.
yes, interstices.
Yes.
So, we take the soil sample to the lab. Are we not disturbing the normal arrangement of the soil before getting to the lab?
Are you what?
Are we going to disturb the normal arrangement of the soil sample?
If you go back to your geotechnical lab and what have you, you have disturbed and undisturbed sample, isn't it? And there is a way by which the disturbance will be minimized when taking sample from the field for porosity tests in particular and other tests. That is what they call core sample, isn't it? So that the disturbance is minimized. Okay, of course it is a disturbed sample, but you can minimize it so that it will approximately be equal to the field value. Okay. Why is it not showing?